They do a lot of things with steppers already on their own.
Yep. Yeah, the various libraries that you can include with it are really useful. It's nice just to have to basically put in the pins that you're using as the output, and one or two other details, and away you go. I'm a firm believer that creativity is finding the best person to steal from.
Hello, Gary.
Hi, Sid.
Yeah, did you pick up the mirror?
I picked up the mirror. It is now.
Oh, congratulations.
Thank you, thank you, thank you. I now have a 20-inch mirror sitting in my sound room.
It should be on your table in the living room.
The wife won't allow that.
Oh, darn it.
No,
You gonna make it into a coffee table?
Yes, I've got two sections of torpedoes from the U.S. Navy from a project I worked on once, and I've got them to be the base of the table, and the mirror is going to be the top, with the mirrored side facing up, and then I'm going to get a flat, transparent piece of glass to put on top of the mirror so I don't damage it. It'll be the only American torpedo 20-inch mirror coffee table in existence.
Is it a ground mirror or is it flat?
Oh, it's ground, yes, indeed.
It's
but it's actually, the figure is poorly done, apparently. But if anybody in the future wants to take it and grind it for a telescope, they're welcome to it.
Only problem with that mirror is the full thickness mirror.
Yeah, it's quite thick.
They're quite thick, yeah.
I don't think it would ever cool down overnight. Maybe by morning, sort of.
That's the problem.
It's probably the heaviest coffee table anyone has ever dreamt about.
Yeah, I hurt my hands carrying it around. It was so heavy. Like, good grief.
Sid, how many inches is the mirror?
Well, let me see. That's like
about 4 inches.
4 inches thick?
Yeah.
Yeah.
Oh wow.
It's a thing of beauty, though.
It's more than 3. It could be 3.
I'll go get it. I have to be very close to it.
Yeah, do confirm it.
Is it a 20-inch mirror?
20-inch, yeah.
Okay, because my 12.5 is full thickness, and it's almost 2 inches thick.
So this has to be more than 3 inches then.
Yeah. This one's thicker than that. It's pretty heavy. I bench pressed it in its cell back into the bottom of the scope when it was out at Pearson after Mark had it coated. It was a hard hold to hold it up while he put the bolts in place.
Gary might need a chiropractor after he tries this.
Yeah, but it won't be in the cell. That was a big heavy metal cell too.
So how long has this mirror been around?
Oh, before my time. That means
it's historic.
That's
put it
right.
That way.
Here you go.
Wow. How big is it?
Really big and really heavy. I'm going to take the virtual background off.
Yes, please.
Yeah, it keeps vanishing.
Did you measure the thickness?
Yes. It's rather
about 3. It looks about 3 and a bit, maybe.
Yeah, 3.
Maybe 4.
Oh, 4. Yeah, I think it definitely is 3 plus.
Yeah.
Yeah, 3 plus for sure. Yeah.
So it's actually a thing of beauty,
It's beautiful.
And it's got the umbrella hole in it already, and it won't blow away in the wind because it's so heavy.
Yes, indeed. If a hurricane comes along, I'll just hang on to it.
Well, Sid did try to sell it as a boat anchor, but no one took him up on it.
No.
But the coffee table angle seemed to work.
Actually, what is needed is the reconfiguring with a low, high grade, maybe 300 carborundum, just small fixing the curve.
Maybe Gary can do that in his spare time.
Oh yeah, he got all that time now.
No, I'm a telescope assembler, not a telescope maker.
Oh, that will be a new project for you.
Yeah, I'm the same, Gary. I'm an integrator, not a fabricator.
Yes.
I came in late. What's the mirror from?
The mirror from a telescope we used to have on a mobile trailer.
Okay.
Long time ago.
Who grounded it, Sid? I can't remember.
Leo Vanderbilt.
Right. Actually, it's in our history, isn't it?
Yes.
It's in the story of the center.
Yeah, if you go on the website and click about, you'll see a history of Victoria Center, and then if you search around long enough, you'll find the history to that mirror.
What was the focal length?
Yeah, you will see trailer there.
Victoria.rasc.ca, click on about.
Okay.
I think it's in one other published book as well. There's a picture of the trailer.
Yeah. I guess that was Leo and Jack were the two leads on that, I suppose.
Then Jack wanted a trailer to take his belongings to Florida, and the mirror got left behind.
Oh.
Here's the torpedo, part of it. Seriously.
Oh.
It's even got the U.S. government thing on it. It's a Mark 48 ad cap torpedo.
Wow.
And there's a cone on the bottom. It's a big cone that goes on the bottom too.
So you have to be very careful, Gary.
Well,
don't blow your house.
I'm not going to tell any Americans that I actually have this, or else I might be in trouble.
Hopefully nobody's watching.
It was 1993. It was
not that long.
20-inch Upsonian that Gene Steves and George Paul completed.
Whoops.
Is that this one?
Yeah, probably that's the one.
Is that all right?
I think they're one and the same.
Is that all right?
Yeah, it's probably a little loud.
Little Barry.
Who's that?
Mitch, somebody, I think.
We can hear
or is that the 20-inch that's the other one that Guy rebuilt and is now up at the center of the universe?
Oh, that's the Jack's original mirror.
Right, but that might be because the other scope was Evan Vanderbilt. So it's like, because they brought that blank back from, what was that telescope making conference that used to be in California?
Oh, I thought he went to Eastern US. That's where he picked it up. In California used to be Riverside.
Yeah, that one.
Yeah, Riverside, yeah.
That's where the blank came from.
Hmm.
Well, folks, it's nearly 7:35. I think it's time to bring this meeting to order. Chris, are you, can I have, please share the screen?
Yeah, please go. You should be able to.
And the other person I want to check in with is Abedin. Abedin, are you unmuted? Can we hear you?
Can you hear me?
Yes, we can.
Okay.
Well, okay, great. Well, we'll get to you in a minute. Thanks for joining us. Abedin is the guest speaker tonight. But to begin with, I'm just going to attempt to launch something here. And
just so everyone is aware, I'm recording the meeting this evening.
Okay, so normally we have a pretty informal meeting or gathering at Astro Cafe, but once every month we have one that is a little bit more formal, and we have a guest speaker, and so that's going to be great. So the normal format is such that I, Reg Dunkley, the current president of the Victoria Centre, will make some announcements, and so will other people. And then our guest speaker, Abedin, will be giving us a talk about meteors. In particular, his topic tonight is the age and present body of Quadrantid's meteoroid stream. And if there's time left over, we will go through the traditional virtual Astro Cafe web summary and have some general discussion as well. So normally when I show this thing, I hope people can see the screen okay. I've been harassing and generating a campaign of shame for more than 12 months trying to get Lord Krishner to recruit a vice president for us. And I'm happy to say that the campaign has now been canceled because we have somebody by the name of Randy Incan standing in. And Randy, thanks so much for being the stepping in to be the vice president. Welcome aboard, and we look forward to showing you the ropes and training you up to possibly eventually, if you're not too frightened, to be the president of our organization. So
don't scare me away.
At any rate, my president's message, I just want to do a bit of a reflection on, I was stringing out some Christmas tree lights, and I thought, gee, what a wonderful opportunity to apply the knowledge that we just gained from the collapse of the Arecibo telescope, because all of those cables fell down, and we did it. I did it in such a sturdy manner that I think my Christmas display will last until the new year. At any rate, I don't have any more remarks to say than that, except that maybe Vice President Randy, do you have anything to say?
I take the job very happily and look forward to working with you.
Great. Okay.
The happiest person is going to be Chris. Won't have to be past president anymore.
That's right. Yeah. And then the second vice president, Margie, have you any thoughts or comments to share?
I do not.
Okay. Is Bruce the Sky News editor?
I don't see his name.
Then treasurer, Deb the treasurer.
I don't see her name either.
Okay. Well, I called Deb earlier and she passed me the balance. We currently have $11,678 in the club bank balance. And membership, Chris.
Sure, we have currently have 249 members with 8 in the grace period, so it means their membership expired in the last 2 months. Just a reminder that Laurie Roche and I have calendars for sale, so if you we still have some left, so if you are looking for a great gift at a really good price, they're $15, and please let us know. I think that's all I have. Oh, and other than AGM nominations, I'll send out the email again in probably another week. But just a reminder, we still have some open positions on council. Plus, if we have some center awards, so if you can think of unworthy nominees, please let me know. Past president at Victoria, or yeah, past pres, sorry, at victoria.rasc.ca.
Okay, thanks, Chris. Is Laurie on tonight?
She's there.
Well, the school program, Sid, and Laurie, Sid, do you want to go ahead?
Yeah, sure. School program is a slow start this year because of the COVID. And so far we had 4 Zoom presentations. and probably a few more before the end of the year. We don't know how it's going to turn out in the spring. I'm hoping that we will be allowed to go in the classrooms, but somehow I doubt it. It's not the same as was in the previous years, but we are doing the best we can. We have joined with FDAO, and it's a good start.
Okay.
Sid, could I ask Sid a question? This is Dorothy.
Shoot.
Is it possible that some nighttime sky viewing at schools might come before in classroom, considering that the kids are outside a lot during the day?
We could do the solar viewing, not the night sky viewing.
Because no clouds.
That's right, no cloud. And also because during nighttime it will be very difficult to keep an eye on who's wearing a mask and who's not wearing a mask. It will be very difficult. So it has to be during daytime. Yeah, that's a possibility.
The kids couldn't get close to the eyepieces though.
Nobody can touch it.
Yeah.
You'd have to set it up so that you're looking through it and you've got a camera on it and you're looking through a monitor and all that kind of stuff.
I think we may have to get David Lee involved.
Yeah, you'll probably need to do that for the first go around anyways.
Yeah. Anyway, thanks for the suggestion.
Okay, thanks, Sid and Lori. Lori, do you have anything else to add? You're muted.
Sorry. Just considering whether or not for the next little bit is to actually see if we can present these programs as free rather than even a little bit of a charge. We did get a Victoria Foundation grant that is helping with the program, so we might be able to put these on for free. And that might bring in, who knows, but it might bring in a few more people into the program. So we'll see. We'll let you know.
Thanks very much. The technical committee is Matt or online? Doesn't sound like it. Website, Joe?
Not a great deal to report. The website's running fine. Facebook group's running fine. I've added a few more reminiscences for Diane's memorial page. And it looks like that's pretty well slowed down to nothing. So that's good. That'll stand as a memorial to her going forward. Online memorial.
Did you get her obit from the Times Colonist to include?
I didn't include it since it's copyright, but I have linked to it.
Oh, you do? Okay, great.
Okay, well, thanks for doing that, Joe. Is Nelson signed in? From our National Council, Bill, do you have anything to contribute?
Yeah, there was actually a meeting yesterday, and Lori was there too, so she'll correct me if I get anything wrong. Actually, there wasn't a lot that happened at it. Phil Groff, he went through the budget for the year and the projected one for next year, which seems like we haven't done as bad as people might think with everything not happening. And some of that has to do with the fact that there haven't been the hugest number of expenditures. The new national website should be coming online early January, I think it was.
January 18th.
January 18th, so mid-January. And that should help a lot if you're trying, because even during the meeting, I was trying to negotiate something on the website just to see where it was. And it was really difficult sort of to find something until I was told, no, it's there. And so I dug a little deeper, and that was when Phil joined in with saying, yeah, it never ceases to amaze him right to the end that website is proving to have its faults. Yeah. So the new one will supposedly be much more user intuitive and easier to do things on, because so many things are kind of hidden on that website that you have to really dig to find if you want to find something. And next year, the GA will be virtual again. I can't think of anything else. Was there more,
and hosted by the National Center, like rather than giving it over to a club to completely do like they did with Vancouver.
Yes.
The Toronto, I mean the National will host it with the help of everybody. So.
Yes, anybody who wants to, I guess, give a hand.
Oh, there is a 2024 action committee for the solar eclipse. Remember that?
No, I must have missed that.
Okay. They're starting early, and there is essays. It's Randy Atwood that is going to be the chair of that committee, and he would like people who'd be interested in helping out. They're looking at a longer term look at what the National can provide at the time, and so I just keep your ears and eyes open. Things will be coming for that. I know some of us might be going down to someplace and not staying in Canada, but okay.
All right. Okay, well, thanks very much, folks. I think we'll get on to our guest speaker. I'm just going to share the screen here again for a sec. And let's see. And okay, so this was from our website. Our meteor shower expert is actually, he might object to that description. But I'm excited to have him here because it's just occurring right before the Geminid meteor shower, and the Geminid source is an asteroid rather than a comet. And it seems that Abedin did his thesis on the age and parent body of Quadrantid's meteor stream. So that is also an asteroid-based meteor system, so they fit in quite well. So I just want to give a bit of background on Abedin. He obtained his master's degree in 2006 from the University of Sofia in Bulgaria. And then he worked at the Bulgarian Academy of Sciences for 3 years. And he started his PhD degree in University of Western Ontario at London. And this is where I first heard about meteoroid streams, as was a presentation at our GA in 2014 in Victoria. And I don't know exactly who it was from Western who gave the talk, but it was very interesting. And so I've been looking forward to that. And so in his PhD work, he determined the age of 8 meteoroid streams associated with a particular comet. And he earned his degree in September 2016. And since August of 2018, he's been a postdoctoral fellow at the Herzberg Astronomy and Astrophysics, working on collisional probabilities and dust production rates in the trans-Neptunian region. So kind of really interesting. So I'm going to leave it there, and I would like Abedin to take the floor. And thanks very much for coming to share us your talk, Abedin.
No problem. So I'll share my screen here. Okay. All right. Can you all see that?
Yep.
No?
Yes.
Yeah, it's looking good.
Yep. Okay. So as Reg mentioned, I did my PhD in meteor physics. So the stream or the meteor shower I will be talking about tonight is only one of the streams which are associated also with comet 96P Mach-Olds. So Reg mentioned that that the quadrantids are linked to an asteroid, but we will see that the asteroid alone cannot explain the observational characteristics of this meteoroid stream. So for this talk, I will first provide some introduction. I wasn't really sure of the background of everyone here. I'll try to keep the talk as simple as possible where I can. So I'll start with an introduction mentioning the relationship between comets and meteoroids and how meteoroid streams are formed. Then I'll also provide some background on the dynamics and how we trace a meteoroid stream back to parent body. And I'll then show some observational constraints of the Quadrantids meteor shower. And we'll then provide the constraints or basically constraints based on numerical simulations, how we find that the age of the quadrantids, here I should have put that the age of the core of the quadrantids is young, and we will get to that in a bit. It's getting very complicated. And it's associated with the asteroid 2003 EH1 and also with 96P, with comet 96P Mach-Olds. So I really have a problem talking about asteroid, but we will get to that in a bit. And finally, I will provide some summary from this talk. So I need to close this window here. So I would like to get something straight right at the beginning of this talk. Meteoroids are and meteor showers are generally associated with comets and to a lesser degree with asteroids. And also, I see a lot of people use some terms interchangeably or incorrectly. So I would like to lay down a few definitions here. And these are meteoroid versus meteor versus meteorite. So meteoroid is an object, or it is basically any object in space, which is 100, which is in size from 100 microns to about 10 meters. But meteor, on the other hand, it is not an object. It is a phenomenon which is in the atmosphere. As the meteoroid enters the atmosphere, because it moves with such a great speed, the part of the molecules from its surface, because it encounters the atmospheric molecules, it heats up and it loses material off its surface. It's called ablation. And if that meteoroid, if that meteor or the meteoroid, I should say, survives the flight through the Earth's atmosphere and falls on the ground, and we recover it, then it's called a meteorite. So these are the few basic terms. So as I said, meteoroids are usually associated with comets. And on the figure here on the right-hand side, we see an orbit of a comet. They vary greatly in size and in shape, I mean the orbits, but they're elliptic. So if you consider an orbit of a comet like this, when the comet is far away from the sun, it's not active. It's just, you can only see the nucleus of, well, we can't really see the nucleus, but essentially it is inactive. As the comet approaches the sun, say at a distance of 5 astronomical units or less, the volatiles in the comet, they begin to sublimate, which is a direct transition from a solid to a gaseous state. And the comet begins to display a coma. The coma would be the gas envelope around the nucleus. And also, as the comet approaches even closer to the sun, we will start seeing two distinct tails, which are here on the left hand side figure. Is a gas tail, a dust tail, and a gas or plasma ion tail here, which is normally bluish, greenish color. And one thing to note is that the plasma tail always points in a direction away from the sun. Perhaps you might have heard that before. Here, let's have a closer look at what a comet nucleus really looked like. So our understanding of comets first came with from the dirty snowball model by Fred Whipple in the 1960s. This is a picture here where Fred Whipple demonstrates to his students what a comet nucleus looks like. So it is composed mostly of water ice, CO2, methane, ammonia, and embedded dust particles inside of this. It's essentially a agglomeration of all that. The dust particles, they range from microns to centimeters in size. So as you can see here in the picture, you essentially take a snowball and you roll it in dirt or in sand, and hence the dirty snowball model. We believe that unlike asteroids, most of the comets are primitive. They have been stored in a really very cold temperatures since the dawn of the formation of the solar system. And this is why, this is one of the reasons we are really very interested in studying meteors, because they are proxy as to their progenitors. So here we have just a few pictures of a comets. The one thing which I would like to point is that comet nuclei are darker than the model that Whipple suggested. From observations, well, we only found that out from spacecraft missions. For example, with the Giotto mission to Comet Halley, with the Rosetta mission and epoxy mission to Comet Hartley. And their surfaces are really very dark, almost as dark as a charcoal. And the activity, the sublimation, is limited to a small fraction of its surface. So what happens is, as the comet approaches the sun, the ices begin to sublimate. The trapped dust particles or sand particles are liberated, and as the gas expands, the particles are accelerated away from the nucleus. And these particles are referred to as meteoroids. Oops. So most of the comets are, today we recognize basically two major reservoirs of comets. One being located just beyond the orbit of Neptune. It's the Edgeworth Kuiper Belt, or just Kuiper Belt for short. And the other one is the Oort cloud. So the Kuiper Belt is about 100th of the mass of the Earth, while the Oort cloud is almost 1,000 times as massive as the Kuiper Belt. And scientists believe that it contains billions of comet nuclei. So although most of those comets reside in these two reservoirs, sometimes gravitational perturbations by planets, or for example, in the Oort cloud, the gravitational tides, the galactic tides or close passing stars would perturb their orbits, and some of these orbits will enter the planetary region. So we believe that the Kuiper Belt is the source of the so-called short period comets, which have periods with less than 20 years. And the Oort cloud supplies the long period comets, or comets with periods which are greater than 200 years. And then there is an intermediate group of comets known as Halley-type comets. These are with periods, these are comets that have periods less than 200 years, but greater than 20 years. So for example, on the picture here on the right-hand side, you can see a long period comet, Ikeas-Junk here, and the Halley's comet. While Jupiter family comets, you can see in green, we have Tempel 1, Comet Holmes, Hartley 2. Their semi-major axes extend up to or close to Jupiter's orbit. So I would like to describe very briefly here how meteoroid streams are formed. So we've touched briefly on that meteoroids are linked to comets, but to be more specific, as the comet approaches the sun and the ices begin to sublimate and the particles are ejected off the surface of the comet, these particles here on the figure on the left-hand side, these particles are ejected with speeds which are much smaller than the orbital speed of the comet. For instance, a typical ejection speed of these meteoroids would be up to a few hundreds of meters. This is, so typically would range between 10 meters per second to 200-300 meters per second, where the orbital velocity is a few tens of kilometers per second. Therefore, meteoroids because of these low ejection speeds, meteoroids will follow orbits which are similar to that of the parent, and this can be seen on the figure on the right-hand side. So this, for example, is comet Encke. Although the comet, you can see the orbit of the comet in white here, and you see its material, the ejected material follows the ejected material follows orbit which is very, the ejecta follow orbit which are very close to that of comet Encke. Over time, the meteoroids will spread along the orbit of the parent, and that normally takes up to 100 revolutions of the parent. So after 100 revolutions of the parent, the meteoroids will occupy the entire orbit of the parent. Also, as this material passes through the Earth's orbit, as we can see here, we will be observing meteor showers. So the duration of the shower or the width of the meteoroid stream, as we can see here, or how long does it take for the Earth to pass through the shower, is highly indicative of the age of a meteoroid stream. So narrower meteoroid streams, we believe that they're younger, whereas widely dispersed or long duration meteoroid streams are old. So what do we know about the Quadrantid's meteor shower? On the picture here, the radiant of the Quadrantids is located in the constellation Bootes here. And the stream was first reported in around 1835. And you can see the Quadrantids annually or every year between January 3rd and January 4th. And please note this short duration for only 2 days, basically. And despite the stream being among the strongest with zenithal hourly rate or ZHR 100, because of the brevity and the fact that it happens in the winter, we don't have many observations. We don't have many visual or photographic observations of the Quadrantids. We are mostly able to see, or not to see, to detect it via radars, echoes from those meteors. And from these observations, we know that the duration and the width of the activity is very narrow, and therefore we think that the Quadrantids are really young. But radar observations show that that there is a broader activity superimposed over that narrow activity. This narrow activity is often referred to as the core of the Quadrantids. And we will see that the Quadrantids, the core of the Quadrantids could very well be explained by origin from asteroid or comet 2003 H1. And the broader activity we will also see that it's linked to comet 96P Mach-Holtz. So the figures that you see on this slide are the activity profile of the quadrantids. On the left-hand side, we have a visual profile, which is the activity profile. So on the x-axis is the solar longitude. You can think of this as time. Essentially, as time progresses, the activity picks up and reaches a maximum value and then drops. So, solar longitude of 282 to 283, this is essentially 1 day. So we can see how narrow this stream is, only 1 day, basically. And the core activity, the shaded area, is only about 17 hours. So the visual activity profile is obtained from the Dutch Meteor Society, and from 1986 to 1992, all the accumulated data. And here on the right-hand side, we have a similar plot, but this is the radar profile of the quadrantids detected by the Canadian Meteor Orbit Radar, which comprises data from 2002 all the way to 2014. Again, you can see the core activity of the shower, but you can now also see these wide wings, or the broad activity of the shower. Excuse me. So how do we find, how do we know when we observe a meteor where it comes from? Or how do we link it to a parent body? From observations, these usually involve either radar detection or photographic or video detections. You need to observe a meteor, the same meteor, from at least 2 locations, which are separated, say, 50 or 60 kilometers away, say, or 100. And we know these locations, the coordinates of these locations. We can measure the coordinates of the meteoroid. So the thing is, when you observe it photographically, there is generally a rotating shutter which breaks the meteoroid, the meteor path, into segments. So from these segments, you can determine the speed of the meteoroid, and also you can determine the geocentric coordinates. Using just a simple triangulation, we can compute the heliocentric coordinates x, y, z, and the speed above the atmosphere. These these coordinates x, y, z, and v, and the speed, then are used to convert that to orbital elements, and we can integrate the orbit backwards in time to find where it came from. So on the figure here, on this figure here, you can see in magenta color the orbit, the mean orbit of the quadrantids. The blue circle is the orbit of the Earth. The red is Mars, and the orange is Jupiter. And in black is the orbit of asteroid 2003 H1. So please note the similarity of the two orbits of the Quadrantids and 2003 H1. That was one of the reasons why this asteroid, or I usually prefer to say object, to 2003 H1 was suggested as a parent body of the Quadrantids. So we used well, the asteroid or object 2003 H1 was suggested well before this work was done. That was, I believe, David Jewett, a few years prior to this work. But here we just confirmed that this parent body is namely the progenitor of the core of the Quadrantids. So once we have a meteoroid orbit, we can then search for the parent body. And as we found out, it's is asteroid 2003 H1, but I will get into that in a second, where right at the beginning, I said that I have a problem with calling this object an asteroid. We can, I will argue that it is actually a dormant or an extinct comet. So once we found the parent body and we know the orbit of the meteoroid stream, we can determine via numerical integrations when and where the meteoroids were ejected. Using the location and the time, we can use the comet nucleus or to create a synthetic meteoroid stream or a meteoroid cloud, and then we can propagate their orbits forward in time and see if the stream will intersect the Earth, and also if it can reproduce the observed characteristics of the shower. So when I say an extinct or dormant comet, or I should say, it's too early to say that an object is an asteroid. There is a really serious problem with that, because we don't really understand how you can form a meteoroid stream linked to an asteroid unless there is another object colliding with this asteroid. And these things, they don't happen very often. And even if it happens, the ejecta speed are much greater than the sublimation driven meteoroids. And these high ejecta, collisionally driven ejecta, they will disperse much widely in space, and will produce much wider meteoroid stream. So an explanation is that 2003 H1, since it doesn't show an activity at present, its volatiles might have just depleted. So this is what we would call an extinct comet. So because basically there is no longer any ices to sublimate, there remains just a dead core. Or the core, there still could be ice, but as the comet sublimates, only the smaller particles can leave the surface. of the comet. The heavier particles will be lifted up, but they will fall back on the surface of the comet and will form an insulating layer on the surface, which will essentially quench the sublimation or the activity of the comet. So we have to be really very careful when we say it is associated with an asteroid. That the same idea holds for Phaethon and the Geminids. So here I will present some numerical simulations that we use to determine the age of the core of the Quadrantids. So we used very high precision orbits or observations of 7 bolides. These are exceptionally bright meteors, and from these observations, we have a very precise orbits for these bolides. These are roughly a few grams, and the largest one that we had was 1.2 kilograms, really bright. And 2 of them, the largest ones, are observed within the core activity. We know that that they were in the core of the activity because they were observed right at the peak of the shower. We use these fireballs or these bolides to create virtual clones or to sample their orbits and to integrate them backwards in time, along with the proposed parent body to 2003 H1. If you only took one orbit or one bolide without any clones, and if you hoped that the 2 objects will, the one bolide and 2003 H1 will intersect sometime in the past, that's probably very unlikely. So that's why you have to do it in a statistical way to investigate when their orbits might have come close to each other. So for that reason, for each orbit pair, each clone of each bolide, plus the parent body, we calculate the minimum orbit intersection distance between their orbits. Because if you're hoping to find a place where the bolide separated from the parent body, you probably won't be able to find that in the XYZ space or in the Cartesian space. So we use the minimum orbit intersection distance instead, plus orbital similarity criteria, which I'll get to that in a second. So just very quickly, I would like to explain what the minimum orbit intersection distance is, or MOID for short. You can see 2 orbits here, 2 elliptical orbits. We have the central mass or the sun here. You might be tempted to argue that the closest distance between the 2 orbits is near the perihelion, or where the 2 orbits, where the 2 bodies approach the sun at the closest distance, but you'll probably be wrong. So the distance, the minimum orbit intersection distance can happen anywhere along the orbit. It depends on the orientation of and the size of the 2 orbits. And because normally the orbits precess over time, the distance, right, in this case, the distance is in this denoted by this yellow line, the minimum orbit intersection distance. It is not constant. It will change at after 100 or 200 years or 1,000 years. The minimum orbit intersection distance might happen here or where the red line is. Another concept which I would like to briefly explain is orbital similarity criteria. It is very, how do I say that? It's very hand-wavy. I'm not very, it's not really a robust way to say if two orbits are similar, but there is a method by Southworth and Hawkins. This criteria essentially, it takes the distance in 6-dimensional space created of the orbital elements and measures how far or how close two orbits are. And this is essentially the method. So if you take these two orbits here in the middle, the two orbits are obviously very different. And if you worked out these numbers here in this equation, they will give you a ridiculous number. An accepted number limit is, for this criterion, is 0.3. And I don't know how they came up with that number, but 0.3 or less, I should say. And as you can see, these two orbits on the right-hand side, these are very similar. So in other words, in this work, I will use the minimum orbit intersection distance and the orbital similarity criteria to check if the Quadrantid's orbit are similar to that of 2003 H1. So in this figure, what you're seeing here is the evolution of the minimum orbit intersection distance of each individual clone. So here we have 10,000 clones, and between 10,000 individual clones and the orbit of 2003 EH1. So the red line is the mean of all clones. And as you can see, so on the x-axis is the time, and on the y-axis is the minimum orbit intersection distance. So we're looking where the minimum of the minimum orbit intersection distance happened, or I should say when. And if we, 0 is the present, and we can see that the distance between the two orbits becomes or gets to its minimum around 200 years ago. And this is a pretty convincing scenario, or it's a pretty convincing method of saying, of trying to determine when is the most likely ejection epoch of these meteoroids. Also, we can compute the relative speed at the minimum orbit intersection distance, and we can see that these are less than 1 kilometer per second. And I would like to draw your attention to that, because I argued in at the beginning of the presentation that the meteoroids are related to comets. And if 2003 H1 was indeed an asteroid and was hit by another object, these meteoroids, they would have these speeds at the minimum orbit intersection distance, they would have been just higher. These ejection or relative speeds at the minimum orbit intersection distance, these are consistent with meteoroid ejection from due to cometary sublimation. This figure is for the same bolide, the same clones, but this is the similarity criteria. Remember when I said that this measures how close two orbits get? And again, we have the time on the x-axis, And this is the DSH, or southward Hawkins criteria. And again, we see that the orbits become much closer, or I should say more similar, about 200 years ago, between 200, someone could argue 200 and 300 years in the past. And there is one more criteria, which is very very similar to Southward and Hawkins. It's called D prime, or criterion suggested by Drummond in 1981, but it's much rarely used at present. And it still gives a minimum around 300 and 200 years. So the results so far look very convincing that the orbits of the Quadrantids and 2003 H1 were very similar about 200 years ago. This is the same thing, but this is for another bolide. And we can see again that the minimum orbit intersection distance happens about 200 years ago, but here we observe a bit higher ejection speeds, or I should say the relative velocity at the moid. And someone could argue and say, well, you just said that the ejection velocities, they should be low if they're cometary, but this meteoroid, this bolide here is not, the precision of this bolide is not as good as the previous one. So the same thing is, so here we are seeing again for the second bolide, the Southward and Hawkins orbital similarity criteria, which again displays a minimum between 200 and 300 years, and the Drummond criterion here. So now that we are pretty much convinced that the shower is young, we can, and using that the most likely ejection epoch, I would argue 200 years ago, but you might argue it was 300 years ago or just 100 years ago. So therefore, we use a range of epochs centered around a given most likely epoch, and we create a synthetic meteor shower. Essentially, we create thousands of particles. We give them some ejection velocity, and this ejection velocity is not just random. Well, it is still random in direction, but the speed is actually given by this equation here. And if you work out the numbers, so R here in this equation, the small r is the heliocentric distance, rho is the density of the nucleus, then R sub c is the radius of the comet, and m is the mass of the particles of the meteoroids. After we've assigned each meteoroid velocity vector, we integrate their orbits forward in time, and using a suitable force model. That means beside the gravity, we also, the smaller particles, they will be subjected to non-gravitational forces. Because they're so small, the solar radiation pressure will tend to push the particles away from the sun, which effectively results in a lowered gravitational force from the sun. There's also another radiation force on particles called Poynting-Robertson drag, or just PR drag for short, which kind of competes with the solar radiation pressure, it causes particles to causes particles orbits to slowly decay over time and fall towards the sun. So having this force model, we follow their dynamical evolution up until the present, and we calculate the radiant position of the shower, and also we construct a theoretical profile based on our modeling. So here is part of these simulations. So we ejected particles in around 1800. So this is the evolution of the orbital node of the ejected particles from 2003 H1, and further back in time. The idea is I need to, how far back in time do I need to go to be able to match the width of the shower? Remember when I mentioned at the beginning that the width of a meteor shower is related to how old a meteor shower is, or a meteoroid stream is. So here we go. So at 1000 BC, we have a very poor match. And I'm starting to go back in time. 3000, 4000, 5000, still bad. And we see we need to go at least like 10,000 BC to be able to match the observed profile, or I should say the observed width of the quadrantids. Of course, you can argue that this profile here is just terrible, but this is just the visual profile, and the meteoroid, the radar meteoroids profile is much more smoother and much more symmetric, and it basically this modeled histogram in red will match much better the radar histogram. Excuse me. And for summary, I would like you to take these notes. The quadrantids are among the strongest annual showers, and with ZHR, or zenithal hourly rate, about 100, which is comparable to the Perseids and the Geminids. The Geminids, which should peak just, I guess, a week from now. But the quadrantids are unique. They're unique because they have very short duration. And because of this very short duration, the core of the quadrantids, based on our numerical simulations, we show that the quadrantids is really young, about only 200 years, whereas meteoroid shower ages, or meteoroid stream ages, they range to thousands of years. But we just saw that the 2003 H1 alone cannot explain the overall activity. It can only explain the core, the very strong, narrow activity. But the broader activity of the shower, we believe, is associated with comet 96P Mach-Olds, and perhaps 96P Mach-Olds, sun-grazing comets, and 2003 H1, they share a common origin. And our simulations show that the origin of the wider activity of the quadrantids must be as old as 10,000 years. Meteoroids from 96P Mach-Olds, they must have been ejected 10,000 BC in order to explain the current activity profile. And I'll take some questions with that. Thank you so much.
Excellent. Thanks very much, Abedin. Can you close your screen?
Yeah. So I should probably stop share, and I can go back to the slides if you have any questions.
Well, I'll just start off. This is all very new stuff to me. I often wondered how you can come to these decisions. It's a pretty complicated and intensive process to figure this stuff out. So it's a lot of hard work there.
Well, it took me 6 years to complete my PhD.
Let's see. Well, there's one other thing I often wondered if these comets lead a meteoroid stream, create a meteoroid stream, what about the Earth? And then you kind of triggered it. The Earth has got such a high escape velocity that it would not leave many particles in its wake as it goes around in orbit. Is that true?
I'm sorry, I didn't get that.
Well, let's say the Earth's atmosphere, if it's shedding any particles in its orbit, or is the escape velocity such that the particles in the Earth's atmosphere are bound to the planet?
So if I understand what you're asking is, if you're asking for gravitational focusing of the meteoroids because of the mass of the Earth, there is a gravitational focusing. In fact, when you observe a meteor in the sky, if you propagate its orbit backwards in time, it will be wrong. It will be wrong because what you're seeing is the current trajectory of the meteoroid. You cannot just extrapolate it backward, like linearly backwards in time. So what happens is, as a meteor comes along, it gravitational, because of the gravitational focusing, it will curve down. And if you just extrapolate it, you will say that it comes from this direction, but it actually comes from here. It's called, in meteor physics, this is called zenithal attraction. And you have to account for the gravitational focusing when you want to determine the orbit of the meteoroid.
Has anyone else had any questions for Abedin?
I have a question. Good talk, Abedin. Like, good grief, this is far more complicated than anybody would think. But I have a really simple question for you. Is most of the velocity that the meteor has entered our atmosphere with due to the speed of the Earth, which is around 70,000 miles per hour? Is that most of it? And how fast are these particles actually traveling through space when we hit them?
Right. So that's a good question. So the speed of the meteoroid in the Earth's atmosphere is a combination of two effects: the Earth's motion around the sun and the motion of the meteoroid around the sun. Then it's just a vector sum of the orbit of the Earth, of the velocity of the Earth and the meteoroid, and based on the we know that the meteoroids can hit the Earth only when they are at 1 astronomical units from the sun. So we know that meteoroids at this distance, 1 astronomical units, they cannot have a velocity or heliocentric velocity greater than 42 kilometers per second. If they had velocity greater than 42 kilometers per second, they will be on hyperbolic orbits. So keeping this in mind, the maximum speed, and also given the orbital speed of the Earth about 30 kilometers per second, the maximum speed a meteoroid can hit the Earth is 72 kilometers per second. That's a head-on collision. Given the meteoroid is not interstellar, given it's within the solar system. So a head-on collision will give you 72 kilometers per second. This is the maximum. But the lowest collision speed is about 11.2 kilometers per second, or which is the escape speed of the Earth's escape speed. So generally, all meteoroids that we observe impact the Earth's atmosphere with speeds between 11 kilometers per second and 72.
Is the 11 kilometers per second where they're actually chasing the Earth or not?
No. So this is, well, essentially, yes. But this is the lowest speed. If you took a meteoroid, and if you take the Earth and put a meteoroid here with 0 velocity relative to the Earth, because of the gravitational acceleration, the meteoroid will be accelerated to 11 kilometers per second.
Oh.
This is the minimum. It cannot hit the Earth with speed less than that if it originates in space.
So is there such a situation where there's meteoroids hitting the Earth from behind as opposed to us blasting through them?
Oh yeah, yeah.
Oh.
Any configuration is possible.
Okay.
Yeah.
Good. Thanks.
No worries.
Anyone else?
Abedin?
Yeah.
A few questions about meteor showers in general. First of all, how many named showers are there through the year?
Oh, I don't know the answer to that. There are a lot, and it depends on. So with the radar studies, with radar detection, so basically radar detections are good for that because we can detect meteors even in all overcast weather. But the radar detections, they can also detect very small meteors and very weak activity. And once we detect the weak activity, we can find the radiant, and then we start calling them by name. We say, okay, these are lambda torids coming from the lambda star of the Taurid constellation. And these are mostly based on radar observations, but the very strong meteor showers like the Geminids and the Quadrantids and the Perseids, they're a handful.
And what proportion of, let's say, naked eye meteors come from showers as opposed to being
a sporadic
isolated
background? So meteoroids which are not associated with any shower, they're called sporadic meteoroids. There is a constant influx of meteoroids onto Earth, which the orientation of all meteoroids is just sporadic. And this is called a sporadic meteor background. And they happen not on a regular basis. Like they happen on a regular basis, there is no correlation between any meteoroid stream. So a shower has to be really strong enough to be above this background, above this sporadic background.
And what proportion of meteors?
I would say
sporadic?
Yeah, I would say above 10.
10% or a factor 10?
10 meteors per hour. If you were looking at the zenith.
All the time, there's about 10 meters per hour.
To classify it as a really good shower.
Okay, and then the last question, the Quadrantid, you said, is very peaked.
Yes.
How wide is a naked eye, you know, of the handful that amateurs might be able to monitor?
Mm-hmm.
What's the full width at half maximum or whatever for?
17 hours.
17 hours is typical.
Yeah.
Cool.
Yeah, so you can see the maximum only within the 17-hour period. But if you remember the wings are normally only seen by radar. These are really small meteoroids, they're less than 100 microns in size. And in order to be able to see a meteoroid by a naked eye, given it will be dependent on the entry velocity of the meteoroid. But for an average meteoroid, I would say about 1 millimeter in size will cause a visual meteor.
That's
anything smaller than 100 and then 1 millimeter will be very hard to detect visually, only by radar.
Thank you very much.
No problem.
Abedin, can I ask a question about the two-component structure for this set? Are there other examples of ones where there's more than one component to a shower? Or is that known?
So that's a very good question. I don't know the answer of this thing, but from my work, I know that some of the showers associated with Comet 96P Machholz, they sort of overlap. So it is very difficult to distinguish, say, this shower ends here and the other shower starts here. But to your question directly, if there is another example of two separate comets contributing to the same meteor shower, I don't have an answer to that. Okay. And plus, we strongly believe, and it's not only my work, it's previous works as well, that Quadrantids, the 96P Machholz, 2003 H1, although 2003 H1 is now dormant, the sun-grazing comets, the Kreutz group of comets, the Marsden group of comets, they all share a common origin. We think there was a huge first precursor, tens of thousands years ago, who first entered the solar system and broke apart into these separate fragments. And because this object, as we saw, experiences Kozai-Lidov oscillation, even if you take the sun-grazing comets that approach the sun very closely right now, if you integrate their orbits in time, backwards in time, you will see that they're actually not very close to the sun. They're currently close to the sun. But back in time, their orbits were very far away from the sun. So the idea is that this first precursor broke apart. Some parts, they just took a different path. And one of the surviving fragments, large fragments, is 96P Machholz. And 2003 H1 could be just another fragment that is now dormant or dead.
Okay, thanks for that. And thanks for the talk. It was interesting.
No problem. You're absolutely welcome.
Abedin, you mentioned the Canadian radar network that studies this. Where is that located?
That's in London, Ontario.
And how many radars do they have to triangulate the?
So we do have two separate at in Canada, like which is operated by Western University. But there are also a lot of other radars across Canada. But these were used by these are specifically by the Western University. Okay. Yeah, and also there are radars which are, well, we can only see meteor showers which are on the northern hemisphere, in the northern hemisphere. In the southern hemisphere, we cannot see all the showers. So there is a dedicated radar system, which is in Argentina, I believe, which we cooperate with them. Like, I mean, when I say we, I mean Canada and Argentina, because Argentina can see all the southern hemisphere showers, and one of the showers associated with 96P, it peaks in the southern hemisphere. We cannot see it from here. It was identified thanks to the Argentinian meteor radar. They provided the data for us.
Good question about radar. What does the radar actually pick up? Surely not the teeny weeny particle itself when it's still out of the atmosphere.
No, no. As the meteoroid enters the atmosphere, it ionizes. It creates a path of ions, and these ions, they reflect radio waves.
Abedin, I was wondering why you were talking about, there's been recently more active asteroids have been found all the time.
Mm-hmm.
And they're recently active, and they're like, they seem to be active maybe for a few months or a year. So are people able to predict any new showers resulting from recently detected active asteroids?
Well, I don't know really. I don't know the answer to that question, but when you say recently active, so the story was, well, these asteroids, I assume, are only active over some given period of time, maybe 2 perihelion passages. So the same thing happened with 2003 H1. We, there's been a lot of work saying that the 2003 H1 is an asteroid, but there was a work by David Jewett and one more person that detected the very low activity on the surface of from the surface of 2003 H1. It happened only once, but I don't think this activity can cause a meteor shower this as strong as the quadrantids. Just the gas drag is not dense enough to lift up large particles.
Could you tell us about the computer software that you use to calculate these orbits? Did you write it yourself? Does it take a lot of compute power to simulate for 1,000 years?
Yeah, so the code, the orbit integrator is not mine. The orbit integrator was written by my former supervisor, and he kindly provided that code. But the analysis of all these data was written by me, and this was like the codes, and this was as a part of my PhD project to develop a meteoroid analysis software toolkit, which is essentially you give me a meteoroid stream. You ask, okay, Abedin, here is a parent body. I give you the parent body, and I want to know if this parent body can produce a meteor shower on Earth, and when, and what would be the radiant, with what speeds these meteoroids will impact the Earth, etc. So I had to develop this code to do that. It took me 4 years to put together. Yeah.
Okay, Abedin, we've got 2 members of our Victoria Center. sits to do located in Victoria. And the other person is Ed Madgen, who lives in the Comox area, a couple of 100 kilometers north of us. They both operate these all-sky cameras and capture meteor tracks on them. If they calculate, they've got sufficient information there to give you the trajectory information of the incoming meteor. Is that of value to you, or is that something you'd be interested in?
Well, it is always a value because the more individual meteoroids we have to propagate back in time, well, it depends if the quality of the data is good, because if it's poor, you most likely will not end up with an accurate like the connection between the parent body and this given meteoroid will not be as accurate. If you have really high precision orbits, then the chances are much better that you link them to a given parent body.
Okay, so if we do get to something we think is precise, you're the guy we should send that information to. Is that right?
Absolutely.
Okay, great.
Yeah, I can tell you where it came from.
Excellent. Well,
Yeah.
It's really interesting. Is there anyone else who has questions for Abedin? Okay, well, thanks so much for taking your time and sharing your expertise with us, Abedin. This is a topic that I don't think we hear too much about, and it's really quite an elaborate process, and find it very interesting. So thanks so much. I really appreciate it.
My pleasure. You're absolutely welcome.
Well, thanks very much.
I'm happy to see that there are people who are interested in meteoroid physics.
Yeah. Well, I will say that John McDonald, who asked a question earlier, and we got involved. John caught a really nice picture of a Geminid meteor, and he continued to take photos, and we have a plume of the evolution of this over about a 30-minute period, which was fascinating, but ruined my Christmas one year in studying this. So it was really fun. And we wrote a bit of a paper for the journal JRASC, the journal of the RASC for it. And I'm still really very interested about this. So I was really looking forward to your talk tonight. So thanks so much for coming.
Thank you so much. Absolutely.
And what we'll do is we'll continue on with a short portion of the meeting. We're just going to review some stuff. You're welcome to stay with us, or we won't be offended if you leave early. So,
okay, so I think it's time for me to retire. So,
well, great. Thanks very much, then.
Thanks a lot.
Thank you. Have a good night.
Okay, so if others don't mind, I'm just going to share the screen again and see if we can get up our stuff. I just want to highlight a few things coming our way. Okay, so that was that. So for the December 7th Astro Cafe, Jim Hesser recommended 3 presentations we might be interested in. One is on the Perseverance rover, and it's a YouTube thing that it was already delivered, and the Ottawa Center and the Montreal Center combined to put this thing on, and apparently I haven't had a chance to look at it yet, but that sounds like it would be really fun to do. And the person who delivers the talk came from Canada, and she was a person who basically is involved with the operation of the various projects. So it should be quite exciting, and the Perseverance system will go in orbit around Mars in the mid to late February, I believe. So it'll be a really interesting topic. It says here it lands on the 18th of February, so that's something. So check that out. Jim also encountered an interesting talk by a person who has been exploring how alternate life forms might be out there if you're interested in exploring that option. And there's if you click on this link here.
Can you scroll up your page, Rich?
Pardon me?
Can you scroll up? We can just see the top, this first item. Or scroll down, I guess.
It's not scrolling at all?
No. Not for me, anyways.
No, it isn't.
Well, there's something weird here. I won't bother showing any more of it. I'll just say that go to the page. There's a a thing on the Perseverance rover. There's a thing on the Search for Life. And there's another thing, talk about eclipses. It's on the 12th of December, just before the December 14th presentation, or eclipse in the Southern Hemisphere. So I'll leave that. I just want to check though, if I change this, can you see a different screen show up?
No.
Wow. What I'm going to do is stop share and I'll try something else here. Just a second. I won't belabor it. I'll just, I know what I'm not wanting here. So.
It depends what you shared. So you can share your whole thing or just one page.
Now, do you see anything now?
Yes, yeah. That's working now.
It's scrolling now, is it?
Yeah.
It is.
Okay. So this is what we've got showing coming up on Wednesday, the December 9th. We have an activity put on by the Toronto Centre that you might want to check. And then Sunshine Coast has got a talk called Shooting Stars and Moon Shadows that you might be interested in. And we have Tim Yarowski got a nice image of Neowise that won the Astro imaging certificate last week. And then there's a talk about the Great Conjunction. With the Great Conjunction, this is a conjunction of Jupiter and Saturn, and it occurs on the 21st of December, and it just so happens that our Astro Cafe is occurring on that night. And we were thinking that possibly, if the weather permitted, it might be good to have the Astro Cafe held a little bit early, and somebody could live stream an image of Jupiter and Saturn. If it was visible, it might be fun to share it on that. So that's December 21st coming up. And I think that's it, except for the week's observing targets is the December 13th is a Gemini meteor shower, which we've talked about. And also on the December 14th is a total eclipse of the sun, which you won't be able to see. So I'll leave it at that, and I'll share the screen and turn it back to you, to the audience. So does anyone else have anything to share tonight?
I just would like to mention that the data sets for the robotic telescope from RASC is now available for purchase for $100. So if anyone would like to process that data, it's a reasonable price and it's a voluminous amount of data. You will need to have a Gmail account of some kind so that you can share the, do a drive share, which is the way they distribute it. So it's not it's not a lump of data they send you. You have to access it online through a share.
Thanks, Joe. Anybody else? Well, I guess that's a no. Well, I guess we'll throw the big switch and sign off. And same time next week, we'll be back with Astro Cafe. So thanks everyone for joining us and have a good week.
Thanks a lot.
Thank you.